Hello, I'm Mr. McBrien, and this is TEJ3M. There are 10 different kinds of people, those who understand binary and those who don't. Let's see if we can turn you into the kind of person who does understand binary today. So Ontario would like for students to be able to demonstrate an understanding of the use of binary numbers, as well as some other constructs of logic and numeracy that we'll get to on another day. So we have this problem. Computers are extremely important to us, incredibly powerful. This has been demonstrated many, many times over the last 60 years. But the problem is that computers and humans don't speak the same language. Today we're going to talk about that. We're going to break apart the decimal system, look at it again maybe for the first time you've looked at it in 10 years. We're going to talk about storing numbers when all we can store is a yes or a no. And then we'll look at how we add numbers in this strange new world. So, as we begin then our discussion, we can talk about what a normal number system is, what the decimal system is. Because of the fact that we evolved to have 2 hands and 5 digits on each hand, we designed a system of counting that reflected this. So the decade, that prefix of deca that reflects 10 things, became the basis of so many things. The decimal system is our conventional number system, and it uses what we call a base of 10. And we designed 10 digits to reflect the number of fingers that we have. Now, we have a 0, we have a 1, we have a 2, we have a 3. I think you know all of these, actually. Once we go beyond 9, then we have to move on. Once we move past then that number 9, we have to start to use more than one digit, more than one character to represent our given number. So how do we do this? Well, we start to keep track of ones, tens, hundreds, thousands, each one having a digit that represents the value of those things. And it's become so ingrained in the way that we work that we take it all for granted. We look at the number 2, 5, 7, and we realize that that's 2 100s, 5 10s, and 7 1s. And this is exactly how we can represent, with only 10 characters, a very large number of things. So we think of that as 2 times 100 plus 5 times 10 plus 7 times 1 equals 257. And you know all that. But you may not think about it very often anymore. Now the question becomes, what would happen if we didn't evolve the way that we did, if you believe in that kind of thing? What would happen if human beings didn't have 10 digits? What would happen if we didn't have 10 different characters to represent numbers? And this is exactly the problem that computers face. Computers only have access to a yes or a no. Their only choice is on or off, 0 or 1. And for this reason, instead of using a base of 10, computers use a base of 2. And there are only 2 characters that can be used, a 1 or a 0. Now, as soon as you realize this, the rest is just mechanical. So we have the exact same approach to considering digits. If we want to represent numbers with a yes and a no, all we have to do is say, all right, we're going to have to use a lot more digits to represent a given number. So let's dissect a binary number now. If we have the number 1011, this represents 1 1, 1 2, 0 4s, and 1 8. And so in binary then, the number 1011, if we convert this to decimal, we have to first convert each one of the digits to its decimal equivalent, then add them together. So we have an 8 plus 0 plus 2 plus 1. So the number 1011 in binary is equivalent to 11 in decimal. Now, in order to make these conversions yourself, what you want to be able to do is design this table of digits, and then simply fill it in with the binary number before you start to do your conversion. So we have a more complicated case here of 101101. And to do our conversion, we can draw the table. Notice that the digits double each time. So 1, 2, 4, 8, 16, 32, 64, 128, 256. You get the idea. When you go to do these conversions, draw this table in ink. Draw it at the top of your test paper, and then you can simply fill in the numbers in pencil each time and erase them. So you draw the table, write in the binary example, in this case 101101, and then just simply add them up. And wherever you've put a 0, ignore them. So in this case, our number 101101 is 32 plus 8 plus 4 plus 1 comes to 45 by my count. So let's try another one. And maybe you want to pause the video now if you think you've got a good idea of how to do this, and simply do this one yourself. Okay, welcome back. Hopefully you followed this process pretty well. As we do the conversion of 100110 to decimal, what we want to do is start on the right-hand side and start filling in the digits on our ink table. So 0, 1, 1, 3 zeros next, and a 1 in the 64 column. As soon as we've completed this process, it's simply a matter of addition from there. So 64 plus 4 plus 2 comes to 70 by my count. Let's see. Oh, but a quick reminder. Work right to left because the number of digits can be different. Okay, 1 times 64 plus 1 times 4 plus 1 times 2 equals, hey, I was right, 70. Awesome. Okay, you've got a worksheet. You can go ahead and work on some of those binary to decimal conversions on your own. All right, so now let's talk about decimal to binary. So whereas we used addition in converting binary to decimal, now we're going to use subtraction to convert decimal to binary. So we're still going to use this table. So hopefully you've got that ink table on your desk now, and you can go ahead and work with me on these things. And what we want to start to do is basically the opposite of what we did last time. So if we want to convert 15 in decimal to binary, we're going to use the table and fill it out from the left-hand side to the right-hand side. So what we're looking for is the first number that is going to be smaller or equal to 15. because that's the one where we're going to put in a 1 to say, yes, we need one of these things. To make 15, we don't need any 128s. We don't need any 64s. We don't need any 32s. We don't need any 16s. If we put 16 in, we've got too much. So we can figure out pretty quickly that we're going to put a 0, a 0, a 0, and a 0 in there. But when we get to 8, we say, oh yeah, we can use one of those. And we put a 1 in for the 8. Now once we do this, this is when the subtraction comes in. So we have to figure out how much of the number we haven't taken into account with that single 1 in the 8's column. So we subtract the 8 that we've got covered from 15. And then we say, okay, there's 7 left. All right, well 7's bigger than 4, so we're going to put a 4 in. We're going to subtract again. 7 minus 4 equals 3. With 3, we're going to need a 2 for that. We subtract 2 from 3, we have 1 left over, and so we need a single 1 as well. So when we're finished, 1 minus 1 equals 0. Good, we've got it taken care of. We've taken care of the entire number. So 15 in decimal is 1111 in binary. The zeros to the left-hand side are unnecessary. You can include them if you want to, or you can leave them out. You only need zeros after a 1 has been put in place, much like when you think about it, the decimal world. Okay, 15 in decimal is 1111 in binary. So let's try a tougher one then. So 66 in binary, again, we're going to work from the left-hand side. How many 128s do we need? Well, we don't need any. But when we get to 64, we are going to need one of these. So we put a 1 in. Then we subtract the 64 to find out how much we haven't taken care of yet. 66 minus 64 is 2. That means we don't need any 32s, we don't need any 16s, we don't need any 8s, we don't need any 4s. But when we get to the 2, we do need one of those. 2 minus 2 is 0. We're not going to need any 1s. And so we found our answer. 66 in decimal is the same as binary, 10000010. And I think you're starting to see that this table, if you take the trouble to write out this table, it makes it extremely easy to do these processes. So let's try one more. Decimal 75 converted to binary. If you want, pause the movie, do this one on your own. If you're not comfortable yet, you can go ahead and watch along with me as I work through this. So 75 is smaller than 128. We don't need any 128s. However, 75 is larger than 64. We're going to need one of those. 75 minus 64 is 11. So we're going to have 0 32s and 0 16s. 1 8. 11 minus 8 is 3. 0 4s. 2. We need a 2 and we need a 1. So the answer by my count will be 1 0 0 1 0 1 1. Hopefully you followed along with that. Okay, adding binary numbers. So remember that numbers are interesting on their own to store, but we often want to process them in some way. We're going to illustrate addition of binary numbers now. Now, before we do this, just like with decimal numbers, we want to analyze, just like when we were dissecting how the numbers worked, we first examined decimal to see how we used to do that. In fact, we want to re-look at adding decimal numbers in order to understand better what we do, and then we're going to mimic that process exactly. So let's consider adding 16 plus 25 in decimal. Well, if you're like me, you consider the digits one at a time. So in the ones column, we have a 6 and a 5. We add those together, and we get an 11. And the 11 is too big to retain in the right-hand column, so we take the 1 and we place it in the ones, and we add a 10 to the tens column. And once we've done that, we can then treat the tens on their own and get our answer of 41. In fact, adding binary is exactly like this. So when we add binary, the only difference is we realize that we carry when we reach 2, not when we reach 10. So doing an example here, if we want to add binary 101 to 11, we have to take each column individually. 1 plus 1, though, is equal to 10. And then we put the 0 in the ones and add the 1 into the twos column. And if you can do this, you can add binary. All right, so the next thing we have to do is consider the next digit. Well, the next digit, 1 plus 0 plus 1, is once again equal to 10. Add the 0 into the twos column, carry the 1 into the fours column. Next thing we do, 1 plus 1 again equals 10. Put the 0 into the fours column, move the 1 into the eights column. And finally, then 1 plus 0 in the eights column gives us 1. So the answer to 101 plus 11 is 1000. So hopefully that illustrates how to add binary. It really is that simple. You can add massive numbers in that manner, just remembering that 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 1 is equal to 10. Oh, and one more thing. 1 plus 1 plus 1 is equal to 1. So if you can remember that, you can do binary addition. Now, along the way here, you may have seen a few cases where you said, wait a second, how do I know which number system was actually used? And this actually can be a source of some confusion. So you can ask yourself, is this number this, or is it this? Right? So we're saying, is this a decimal number, 101, or is it a binary number, 101? In which case, this would be the number of dogs. Well, the good news is we have a trick for communicating this. 101 with a subscript of 10 is that 101 Dalmatians. 101 with a subscript of 2 is 5 Dalmatians. So if you want to communicate, we will typically use text to indicate whether a number is binary or decimal or hexadecimal for that matter. But if you're not sure, you should be able to see a subscript here as well. Okay, so key points from today then. Binary numbers allow us to store numbers using a series of just 2 digits, which is compatible with the requirements of computer storage and processing. Converting from binary to decimal is a series of multiplication and addition steps. Converting from decimal to binary is a series of subtraction steps. Adding binary numbers, we use a carrying digits technique that is just like the decimal system. All right, for your homework then, go ahead and complete the binary worksheet converting to and from binary and addition of binary. If you're looking for some additional challenges, go ahead and try some experiments. See what happens when you multiply by 2 in binary. See what happens to a number when you multiply it by 4 in binary. What happens when you multiply by 8? And how does that compare to the decimal system? I think you'll find some interesting results there. Thanks very much. Have a great night.